At our CFU for chapter 2.5, where we're just going to take a look at whether or not distributions can be considered approximately normal, and we can use normal distributions and normal calculations to calculate them out. So in this first problem, it just kind of allows you to just various methods on how to check. So on this one here, it says density of the Earth. In 1798, an English scientist, Henry Cavendish, measured the density of the Earth several times by careful work with a torsion balance. The variable recorded was the density of the Earth as a multiple of the density of water. Here is Cavendish 29 measurements. So it says, enter these data into your calculator, make a histogram, then calculate out one variable statistic, describe the shape, center, spread of the distribution of the density measurements. So this is going to take a little bit of work and time. So pause the video for a second and enter in these 29 data points into your calculator and come back. Alright, hopefully you have your 29 data points into your calculator. As I'll show you I do, stat, edit, I have mine in here. So we got a few things we want to do. First of all, you're asked to calculate one variable statistics. So I'm going to record the mean, the standard deviation, and down here my 5 numbers summary. So I'm actually going to write all those down just going across here. So my 5, whoops, I apologize, I was on the wrong function. I always think I'm on writing, but sometimes it's on something else. So let's see here, 5 number summary. The numbers are 4.88, 5.295, 5.44, 5.165, and 5.85. My mean, 5.44, standard deviation, about 2207. All right, or 5541 with the mean there. So I've at least noted my data for one variable statistics. So now it asks me to do a histogram. When I look at this histogram, there's many different ways you could do it. So I look at the low and the high, 4.88 to 5.85. So depending on how you want to go about it, what I'm going to do is I'm going to break my graph here, and I'm going to start at a lower bound that seems to kind of make sense. I'm going to just start at 4.8. And I'm going to count by 0.15s. Maybe kind of the thought process here is, if I go 5.85, divide or subtract the low, roughly 4.88, I'm just a little bit above 1. If I divide that by, say, like 7, okay, it ends up being like 1.4. So I'm going to make my bin widths a little bit easier, and I'm going to go 1.5s, or 0.15s, I should say, not 1.5s, 0.15s. This should be 1.4, 0.14, and it's got some decimals to it. So I'm around to 0.15. That's kind of where I'm coming up with it. So 4.95, sorry, I hate it when my 4s don't like to write. 5.1, 5.25, 5.4, 5.55, 5.70, 5.85. Since this is my high, I'll have 1 left here, and then this will be at 6. So that's where I'm getting the bottoms. My tops, these are my frequencies. How often do these scores occur? So 2, 4, 6, 10. I'm hoping that my bins don't go, whoops, I wrote an 8. It's funny, got ahead of myself, 6, 8, 10. And I just want to graph these. Now what I'm going to do quickly is actually do this in my calculator. I know this is something I haven't shown you before in class, but I'm going to use my calculator to help myself do a histogram. So really how you can do a histogram quickly on your calculator, so you can go to stat plot, want to turn the first one on, and as you can see I already have the histogram highlighted. So you want to go to histogram. Whoops, that one, highlight it and hit enter. So second stat plot, highlight your histogram. Then what you want to do before you graph it, go to your window and set your window just like I did here. Notice how I have a low of 4.8, a high of 6, and my bin width is my X scale. Y min, I might make that like negative 3. Y max is my frequency, how high I'm going to go, 10. Then I can go ahead and hit graph, and it will give me my histogram. So then when I hit trace, it will give me my bin heights here. So I go 1, 1, 10, 6, 7, and then 2 and 1. So it goes 1, 1, 1, 10. Let me go back here so I get these. So 1, 1, 1, 10, 6, 7. Okay. So I'm just kind of noting those in my head here. 1, 1, 1. Then it was 10. Then it was 6. Then it was 7. Then it was 2 and 1. I got my histogram. If you want, you can go ahead and write these numbers on here. 1, 1, 1, 10, 6, 7, 2, 1. Then it says, describe the shape, center, spread of my distribution. Okay. So let's draw my curve. Well, I don't see any like major skewness in one direction or the other, so we'll say our graph or our distribution is fairly symmetric. So that means I'm going to use the mean and standard deviation with a mean of 5.441 and a standard deviation of 0.2207. Now here's a nice thing too that you can kind of use kind of as a guide for symmetry. It doesn't always work because you could still have an outlier skewness that could cause this to happen. But look at my mean and my median. They're really close to each other. We know that symmetric distributions, they're going to be equal. Here they're relatively close. All right, so that takes care of A. B now says calculate out the percent of observations that fall within 1, 2, and 3 standard deviations of the mean. How do these results compare to the 68, 95, 99.7 rule? So we want to start off by looking at within 1 standard deviation. So what we're basically going to do is we're going to be going 0.5441 plus or minus 0.2207. So I'm adding and subtracting that interval. So if I take my calculator and I go 5.441 minus 0.2207, I'm basically looking at scores that are at 5.23. I'm just going to round up. I'm going to include that value. And then the other one would be 5.661, so 5.67 or 66, because 67 wouldn't be included. So any values are in between those, including those. So what I'm going to do right now is I'm going to take my calculator, I'm going to go to my stat, and notice how in number 2 and 3 you have this sort A, sort D. This will sort it in ascending or descending order. So I'm going to go ascending because I'll go from smallest to highest. They'll say done. I'm doing it on list 1. So now when I go to stat and I can go to edit, I want to count how many scores are in between these values. So right now if I look here, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 22 scores. So I have 22 scores out of 29, and that is about 75.9% of the scores. So compared to 68, it's a little bit on the high side. Now I'm going to do the same thing to be within 2 standard deviations. So if I'm talking about being within 2 standard deviations, I'm really, if you just trust my estimation, I believe it's between 0.499, so I'm just adding and subtracting 2 of these standard deviations to 5.44, so I'm going 5.441 plus or minus 2 times 0.2207. So I believe it's from 4.99 to about 5.88. So I'm going to look at how many of them are within that interval. So if I go back to my calculator, I'm going to actually, I know on the high end, just looking at my max value, I'm not going to have any, but on the low value, I do, whoops, I forget that that does that. 4.88 is not actually in there. So within 2 standard deviations is 28 out of 29 scores, which is about 96.6%. So I do the same thing with the last one within 3 standard deviations. This is about 4.77 to about 6.10. Okay? Well, that's actually all of them, 29 out of 29, which is 100%. So all the scores are in there. Now, how close is this to the 68, 95, 99.7 rule? Well, it's not dead on, but for the most part, if I look at this, they're fairly close. So I'm just going to note these are close to the 68, 95, 99.7 rule. Maybe, but maybe for except maybe the first standard deviation. All right, so now the second thing that you can take a look at. So we saw that it's fairly symmetric. Right now our numbers are at least pretty good with the second and third standard deviation, a little off with the first standard deviation. But our best way to check is doing this normal probability plot on our calculator. So what we want to do on our calculator is we're going to be graphing the densities versus a corresponding z-score. Now we don't have to convert them all to z-scores. Our calculator will actually do this for us, which is really nice. So if I go to my stat plot, go back to number 1, turn it on, let's go to the last graph, which is the normal probability plot. Now when I hit graph, I'm going to have to zoom 9 to make it fit nicely for us. And we take a look at our graph here, and for the most part we have a fairly nice linear pattern. It's crossing the graph right here very close to the middle. Both the upper bound and lower bound, or above the axis and below the axis, tend to be fitting the data pretty decently. So what we would do is, I know it says to do a sketch, so boom, 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 we have a lot of points in this area, and it kind of levels off. Just want to show kind of what the general pattern is. My biggest key is, can you tell me that this is your densities, your x values, and this is your z-score? So we just want to know, is it a linear pattern? Is it crossing at the x-axis in the middle? Do the values above and below seem to be balanced? So just want to write that description in a sentence or two. So the normal probability plot is roughly normal. Or not normal, sorry, roughly linear. What am I thinking? And crosses the x-axis at the center. It has roughly the same number of scores above and below the x-axis, which suggests this data, or I should say this distribution, is approximately normal. All right, so D, having inspected the data from several different perspectives, doing a normal plot, analyzing 1, 2, and 3 standard deviations, write a brief summary of your assessments that combine your findings from A through C. So I would just say something to the extent of this. Is it approximately normal? Yes. We would consider this distribution to be approximately normal since all 3 methods gave us no evidence to suggest otherwise. So in the first method we graphed it. It looks symmetric. In the second method we analyzed 1, 2, 3 standard deviations away. It was fairly close, nothing that was standing out. The fourth method, we did the normal probability plot, which is probably the best, fairly nice linear pattern, all the data points above and below, crossing the x-axis right at the center. So we would definitely say by all 3 methods we could consider this data, at least this sample, to be approximately, or this distribution to be approximately normal. All right, let's take a look at the last page. Number 2 gives you a normal probability plot. Here it says the figure below is a normal probability plot of the emissions of carbon dioxide per persons in 48 countries. In what way is this distribution not normal? Okay, well, probably the biggest thing to find out, as you can see, CO2 levels basically.
Good morning,
and
Hopkins High School
Z-score.
staff. At this
Sorry about
time,
that.
the homecoming parade is about to start. So please go down to the Lindbergh Center. Again, at this time, the homecoming parade is about to start. So please go down to the Lindbergh Center. Thank you.
So, anyway, sorry for the announcement about the homecoming parade. So, what I'm going to do is look at where the z-score is 0, because that will tell me how many values are above and below. Okay, roughly that looks the same, but is it a linear shape and is it balanced? No, it's crossing the x-axis right here, which suggests the data is much more spread out. Okay, and or at the center here, which suggests that the data is more skewed to the right than it is normal. Plus you don't have that nice linear pattern. So here we go. So let me just summarize that. So the shape of the normal probability plot suggests that the distribution is skewed to the right. The spread of scores above the
Attention,
x-axis
all Hawkins High School students, the parade is going to start in 1 minute. Please come down
Is
to the
much
mall. Again, all Hawkins
greater
High School students, please come down to the mall. The parade is going to start in 1
than
minute.
the spread of the data below 0 or below the x-axis. All right, this ends CFU 2.5.